Let's look at an example of a place where you need a change of coordinate matrix. So change of coordinate matrices work when we have a vector space, polynomials of degree at most 2, and you have two different bases. So here's the canonical basis, and here's another basis. So let's imagine for some reason you're more interested in the basis where one of the basis elements is x minus 1, and one of the basis elements is x squared minus 1. So for some reason you want polynomials that have zeros at 1, right? And so how do you move from representing v in terms of one basis to another? And the answer is you need something called a change of coordinate matrix. So just to start with, you could think about v as being, right, obviously an ordered basis. You'd start with your first element. This would be 3 of your first basis element, 1, plus -1 of your second basis element, x, plus 2 of your third basis element here. And so the matrix representation of v in terms of beta is going to be 3, -1, 2, right? Well, how would you then, let's imagine you already had this, you'd been working in that basis, and you really wanted to get v beta prime. Now, you could sort of back convert this into this, and then you could write it in terms of that set of basis elements. But is there a faster way? Let's imagine you had, say, thousands of elements and you wanted to convert them from one to the other. And the answer is yes, you can do it. And in fact, all you'll need is this special element, Q, which is defined to be the identity map on your vector space going from beta prime to beta. Okay, well, let's think about what that is. These are three-dimensional vector spaces, so we're just going to have a 3x3 matrix. And you just need to tell me, hey, what does the identity map do on all of the basis elements of beta prime? Okay, so what does it do on 1? What does it do on x? What does it do on x squared? And I need to describe that in terms of the new basis elements, right? The identity map on the first element here, what does it do in terms of 1, x minus 1, and x squared minus 1? Well, it's pretty clear cut that if you're trying to write the identity element, the identity map on 1, you're going to get out 1, right? That means you probably have one of those, and none of those, and none of those, right? Those are your coefficients in the new basis. If you have x, it's pretty clear you're not going to have any x squareds needed, right? But the only way you can get an x is if you have one of this basis element, right? And if you have one of those, that basis element, you get 1x and -1, which means you need 1, 1, so that this side is equal to x, right? X minus 1 plus 1 is x. Okay, last but not least, if you're going to get an x squared, the only way to do that is to have a 1 here with x squared. Now, you don't need any x's, right? But if you have this, you have x squared minus 1, so you need 1 extra here. So what is that linear transformation represented in those two bases? Well, you've got to take this, that's the first column, 1, 0, 0, 1, 1, 0, 1, 0, 1. And it turns out what we're going to do here is we're going to say you can represent V in the, this was beta prime, I'm sorry. I was representing this in beta prime, and I'd like to know what it is in the thing that I want. So the thing that I want, I can represent it as Q times the representation in the old basis. So this is V beta prime. So this matrix I know, that's 1, 1, 1, 0, 1, 0, 0, 0, 1. And this I know, that's 3, negative 1, 2. And I can multiply that out. It'll be a 3 by 1 matrix. So 3 minus 1 plus 2 makes what? 4. Then I've got 3 times 0, negative 1 plus 0. And then here I've got 2, right? So there is my matrix. What does that mean? When you see this, you think that V can be written as 4 of the first basis element plus negative 1 of the second basis element plus 2 of the third basis element. That's a minus. And you could multiply all that out and you could see that that really is V. So this change of coordinate matrix does exactly what I'm hoping for it to do, okay? Now, what we need to do here is I need to present to you a theorem that says this always works this way. Let beta and beta prime be two ordered bases for a finite dimensional vector space V, and let Q be this matrix, just like I chatted about before, except for that prime is supposed to be right there. Apologies. And I don't know why it's having trouble with my prime. My prime is supposed to be right there. Okay, so I need to make two arguments here, okay? So the first argument is if you define it this way, Q is invertible, okay? The second thing I need to argue is that the representation of V in terms of beta is equal to the representation of V in terms of beta prime times Q, defined like this, okay? So for part A, proof of A, think about this. IV, that's the identity map, is invertible, right? So Q is invertible by a previous theorem. In our book, it's theorem 2.18, right? If the linear transformation is invertible, so is the matrix representing it. So Q is an invertible matrix. Proof of B. By the way, I didn't leave much space here because both of these proofs are pretty straightforward. They're just sort of thinking about what I actually have here. So remember, this is the matrix representation of a linear transformation. So we can really talk about that, okay? So the vector V represented by beta is equal to the identity map, right? What's the identity map on V of V? Well, that's exactly V, right? So that's true, right? But what do we know about this? We went to great pains to prove that is just equal to, this is true for any linear transformation, it's equal to the matrix transformation going from beta prime to beta times V in terms of beta prime. But that is just Q by definition. And so really what we're doing is we're appealing to the work that we've done with general linear transformations and the matrix representations of them, and we're saying, hey, this is just a special one, just happens to be the identity transformation. And so that's what we've got there. And then this Q is exactly what the title of the section is. Given beta and beta prime two ordered bases for a finite dimensional vector space V, the change of coordinate matrix Q equal to this and again, my typing is off, beta prime is at the bottom, beta is at the top. That matrix is the one that that we care about. That's the change of coordinate matrix, and we say Q changes beta prime coordinates into beta coordinates, okay? So that's a good place to let off, and you can think about this example, and hopefully that's instructive.